We will invite our first speaker here, Professor Cowan from the University of Liverpool and from the Stephenson Institute for Renewable Energy. The group of Professor Cowan is mainly focused on the development of catalytic materials for the electrocatalytic reduction of CO2 and also for water splitting. And also he's specialized in surface spectroscopic investigation in these processes. So, dear Professor, the audience is all yours.
So thank you. Before I start, can I just check people online can actually hear okay?
Yes.
Can't hear anything at all, or they can hear perfectly? We're going to assume they can hear perfectly. Thank you. So, excellent. Thank you for the kind introduction and thank you for the invite to be here today. It's been a really interesting few days here as part of the SEAFUEL project, seeing everything that's been achieved, and I think huge congratulations should go to Pal for the way he's managed that project and what's been delivered so far. And it's also been really interesting so far to hear a little bit about SOLAR2CHEM and to see some great posters and some great work. And it's quite remarkable how much things have been done in a very short space of time since it's been running. So as you've heard, I'm Alex Cowan. I'm from the University of Liverpool, in particular the Stevenson Institute and the Department of Chemistry. And I lead a group which we call the Sustainable and Solar Fuels Research Group, and rather annoyingly, perhaps for this meeting, I'm not going to talk about the use of sunlight at all, so perhaps I've missed the target audience here slightly. Will this work? So just before we kick off, what are sustainable fuels? I'm probably telling you what you already know, but just to reiterate, we're interested in any sort of fuel and its generation and the study of it, which can be made using intermittent renewables. So in particular, today we're going to care about solar energy, but it could be wind energy for many of the systems we're looking at. We're going to talk about electrocatalytic systems. You'll be aware that there's a large number of solar fuels under consideration or sustainable fuels under consideration. So we've heard about hydrogen. We obviously know about carbon-based fuels, and that's what I'll focus on today, but also increasingly nitrogen-based hydrogen carriers such as ammonia are of interest too. And the key is that when we utilise our fuel, we get our energy back and we regenerate our feedstock. And hopefully this is done in as close as possible to a closed loop system. Of course, it will never be fully closed loop. As you've heard, we're interested in quite a number of different aspects of this. Today I'm going to be talking in particular, sorry, I'm just going to turn on a pointer on here. Today I'm going to be talking particularly on our work on CO2 reduction, and we do a fair amount of work on trying to do surface spectroscopy of CO2 reduction, but today I'm actually going to talk solely on catalyst development and catalyst utilization. We also have interest in the group in studying water oxidation electrodes, and that's a long-term interest, particularly using transient spectroscopies. And in recent years, working with Andy Cooper at the University of Liverpool and also Dave Adams at the University of Glasgow, we've started to investigate the photophysics and photochemistry of polymer photocatalysts for hydrogen evolution, and also to a lesser extent for water oxidation. And again, this has been done using transient spectroscopies, transient visible and also vibrational spectroscopies. And the common underlying theme of all these materials is a couple of basic reactions: water oxidation, hydrogen production, or CO2 reduction. So let's focus in today on what we're going to be doing. So we're interested in CO2 reduction, and I'm going to be talking completely about developing CO2 electrolysis. So we're going to have a cathode for CO2 reduction and an anode for water oxidation. And we all know the drivers for this. CO2 needs to be seen not only as a waste molecule, it's also potentially a valuable, useful resource. There is, of course, concerns about how long you store your CO2 in a product, but what we need to start to do is to see that in taking a carbon-based material and deriving it from carbon dioxide, we're displacing the generation of these carbon products from fresh virgin fossil resources, which is the current pathway. We're going to be very interested in making one particular CO2 reduction product, carbon monoxide, but as you'll see, there's a huge range of different products we can make, and that presents a challenge in catalysis. If we make a range of products, we're going to need to try and purify our product stream. That brings costs in both energy and monetary. So we want to try and do this in as clean as possible way, making as higher selectivities as possible. And we're going to focus in on this very simple 2 electron, 2 proton reduction of CO2 to CO. Our main competitor reaction is, of course, proton reduction, and particularly the conditions I'll be talking about today. So I'll be focusing in on trying to work in some slightly unusual conditions for CO2 reduction in acid. So we'll be talking about competition with hydrogen evolution. And if I get time at the end, power assures me I've got several hours to talk on, so sorry about that. I'll go on to some water oxidation work that's been drawn in from the SEAFUEL project as well, so hopefully we'll get a chance to talk about that. You'll all be aware that for CO2 reduction, there's quite a number of cathodes being explored, and in the sort of area of metals, there's a lot of focus on a few simpler metals, so silver and gold for carbon monoxide production in particular. And these, of course, have been known to be effective and selective for many, many years. So we can go back to the sort of really key works of Horry, and people have taken this on and they've developed a much better understanding of how these catalysts work, and they've also developed improved selectivities and current densities by doing things such as structuring, alloying, and so on. What we're interested in doing is not working on metal electrodes, but working on molecular electrocatalysts, and to see if we can exploit some of the benefits of these. So small molecules that would typically be used dissolved in solution when they're first discovered. But by the end of the talk, we want to be translating these into an electrolyzer. So I guess the first question is, why bother? We've got some very good metal electrodes which work particularly well. So, for example, we know we can get Faraday efficiencies in excess of 90% at good current densities for a CO2 reduction electrode based on silver. And the overpotentials are not ridiculous. They're actually not the big problem. Well, I think one of the main drivers for our interest comes from this. It's been known for a long time, but I think Matt Cowan really sort of described this in one of the most clearest ways in this nature communications perspective, where he describes there's a basic question controlling the potential utilization of CO2, and that is that many of the CO2 reduction systems utilize an alkali environment, and that's beneficial because it suppresses the hydrogen evolution reaction, of course. There's less protons around, and then we can get higher CO2 reduction yields. We all know from our undergraduate chemistry and even our school level chemistry that carbon dioxide, in the presence of hydroxide, we're going to form carbonates. And that causes us a problem. We've now got to take our CO2, purify it often, and we're going to place it into our device. And here we're going to talk mainly about gas diffusion electrodes. So the CO2 is going to be brought through the back of a porous electrode. And I should just say this is important, otherwise we can't get to the high current densities. If we use a conventional planar electrode in liquid, the solubility of CO2 in the order of sort of 30, 35 millimolar means that we can't get a stable current density of more than sort of 10 to 15 milliamps per square centimetre unless we really start to stir the solution quite hard or agitate it in some way, which of course comes with an energy cost. So we're going to use these gas diffusion electrodes. We're going to pass high concentrations of CO2 through the back of a porous electrode where our catalyst is going to be sitting. And the reality is that a large amount of this CO2 is going to be lost into the electrolyte. And in fact, it gets slightly worse than that. If we start to think about what happens, we're not just going to lose the CO2 into the electrolyte, we're going to consume hydroxide. So we've got a gas diffusion electrode in contact with a liquid electrolyte, so a strong base. We're going to consume some of the hydroxide, and we're going to then need to replace this as an energy cost, of course, in generating the hydroxide. System will probably be using an anion exchange membrane between the two electrodes, and then our carbonate can cross over and it can go to our anode. And now we've contaminated our otherwise pure oxygen gas stream, so we've lost value there. Pure oxygen has a value, so we don't want to be doing that. So it's generally thought that if we work with a concentrated base, the best we can do in this sort of cell design would be to get about 1 in every 2 CO2s converted, the other one would be lost. That's a big cost. We can, of course, go near neutral, so we could use a bicarbonate-based electrolyte so that we can get a steady state near neutral operation. That's fine. We're still going to lose some of our CO2. It might not be quite as bad. We're likely to lose some of the Faraday efficiency. And we have a secondary problem as well that we need to be aware of, that these carbonate salts and bicarbonate salts can actually form in the pores of the gas diffusion electrode. So I've got this wonderfully designed gas diffusion electrode. There's fantastic science going into modifying these to control the wetting of these, to control the gas diffusion, and then I might get salt crystals in them. And then the device will fail. And that's one of the big causes of device failure. So we really want to avoid carbonate if we can do this at all. And this comes from this figure at the end from a very nice science paper that's recently come out from Ted Sargent's group on working in alternative conditions, namely acids. And they highlight that for a high pH system. This is for ethylene production. In their analysis, carbonate regeneration is 55% of the system, is 55% of the operating cost. That's pretty significant. So I think we need to be aware that there is problems if we work using our current device configurations, and that's being accepted. The other point about the near neutral systems is that, of course, at high current densities, we're consuming the protons at the electrode surface, whether we're doing CO2 reduction or proton reduction, and the local pH will jump up. So we'll get carbonate formation forming even at the cathode surface, even if the bulk pH is lower. So can we just do it in acids? And there's some really nice work on this coming out, and it's starting to appear. I think there's a paper from Mark Poper that I'd recommend everyone has a look at, this Jack's paper here. Sorry, when I turn around to look at the screen, it loses the microphone, so it's a little bit tricky. There's this really rather nice Jack's paper here, which I suggest you have a look at. And it describes a pathway potentially to work with some metal electrodes to try and do CO2 reduction. That if we can utilize and decrease the local proton concentration using, by having our metal electrode reducing CO2, we can do this at high current densities, then potentially we can improve the Faradaic efficiency. And indeed, you can do that. If you take a silver electrode and put it into an acid-based system, and then you increase the current density, you'll see the Faradaic efficiency start to improve towards CO production. And that is one possible pathway. But even at, this is data we took in the lab the other day, even at 100 milliamps per square centimetre, here's my CO Faradaic efficiency for a nice silver electrode, a benchmark one. The same electrode in the basic system was giving us about 80 to 90% Faradaic efficiency. We're getting very low, and we can compare that to where we'd be working in the higher pHs. The other thing we could try and do is increase the amount of CO2, or we could try and buffer the local pH, and that's what Ted Sargent's work does. It's a very nice approach, but we still need to be aware that we're going to get local carbonate formation with the problems I've just talked about. Or we could try and improve the catalysis of the actual CO2 reduction catalyst. So very much along the lines of Mark's suggestion, and try and out-accelerate the hydrogen evolution. And perhaps this is where a molecular electrocatalyst could work. We can tune the local binding environment. So that's just the Ted Sargent work I just sort of flag up. This is probably the state of the art. This is for ethylene production. You can see that for total carbons, they're forming around about 40% Faradaic efficiencies in an acid environment by forcing up the local pH, and in this case by using a very high concentration of potassium in their system. So we started work thinking about this on a manganese complex, and the reason we started work on this was primarily because we had it in the lab. We've, as you've heard, done quite a lot of surface spectroscopy, and if you're interested in that, we do some frequency spectroscopy to look at the catalyst when it's closer at the electrode surface. And working on this manganese complex for longer than I cared to admit, and it sort of helped along the way to work out this mechanism. Just many groups. We thought it would be interesting because one of the things we noticed when doing the surface spectroscopy and also sort of other studies was that generate the catalyst in a production steps, this active catalyst, and it's got two possibilities. It can be protonated, hydride, or you can bind CO2 and rapidly proton down via this pathway. You might think that increasing the proton concentration detrimental then to the CO2 reduction efficiency. This catalyst is a little bit unusual, but it won't actually bind CO2 unless there's a strong enough acid source present. And as you increase the acid strength, you actually push the system away from protonation towards CO2 binding. So it's kind of, to us, initially counterintuitive, but really sort of much smarter people who do theoretical chemistry explain this and why this happens. With stronger acids, we get higher CO2 turnover. We thought, well, this could be interesting. Let's give this a shot. So it was developed originally to work on non-aqueous solvents, but you can just very simply deposit the catalyst onto a carbon support. This is a planar electrode, and we put some carbon nanotubes in just to get the surface area up. And I'm not going to go through this in great detail, but say the reds with carbon dioxide present, the blues under argon, and you can see quite a large current enhancement. And we produce CO, not in fantastic Faradaic efficiencies, it's about 2 to 1 CO to hydrogen. But we do this at reasonable onset potentials at neutral pH, and we're quite happy with those sorts of current densities on a planar electrode. So we did that for a number of years and thought that's rather nice, and we put that to one side. And then we sat back and thought about, well, can we take this dependence for the this behaviour in the presence of organic acids, where we can slow the strength of organic acid on the catalysis into water? So we made a water-soluble version of the catalyst. And this was primarily because, well, it was for a number of reasons, but the main advantage, I guess, was that it allowed us to work on inert electrodes, so get away from carbon, which, although we think of being as inert, will produce hydrogen at quite negative potential. So now we can do experiments on mercury and mercury amalgams, which the students love when I tell them they're working with mercury. It allows you to work at really quite low pHs. And now you can see the behavior. Black is under nitrogen or argon, red is under CO2. And you can see that we see quite a large current enhancement for CO2 reduction at any pH below 9. And actually, we can still see pretty good improvements in current density. And we can see quite a lot of CO produced down to about pH 2.5, pH 3. So this catalyst seems to work reasonably well in moderate acids, not very strong acids. That was nice again, but of course this is still at a planar electrode. And look at those currents. This is with a mercury, I think this was a mercury drop or a very small mercury amalgam. But you can see we're on microamps, really no use to anyone. Quite fun from a fundamental point of view, but we need to take this further. So can we put it on a gas diffusion electrode? And Mark Robert's group's sort of shown that we can do this with molecular electrocatalysts, really led the way putting some cobalt and iron catalysts onto the surface. So there's been a few studies now with molecular electrocatalysts on gas diffusion electrodes running at high current densities. So could we do it with manganese? So we just now take our carbon support, a porous commercial gas diffusion electrode from the fuel cell community. We put our manganese complex on with its extra carbon filler. We mix it in with PTFE and Nafion to get the wetting right. There's a remarkable amount of work I never realized you had to do in controlling that. And we set this up with the flow cell, so it's a liquid electrolyte here. And this is what the cell looks like, and this is some very nice work. And I hope Gaia Neri is able to join you later from Enapta via video link. She was hoping to be here, but unfortunately she can't. This is work she actually instigated in our lab just after finishing her PhD as a postdoc. And what's quite nice is, forget the nickel catalyst for a moment, we're going to come back to that. Here's my silver electrode, here's my manganese electrode, and you can see that we're getting an okay current density. It's not great by any stretch. These are quite low over potentials though. If you work it out, we're around about 0.5 volts RHE, minus 0.5. Our manganese catalyst seems to be outperforming our silver benchmark, so that's a good sign. And apologies, that's a little small, and the people in this room can't even read that because it's pixelated. But if you're online, you can probably see that this shows the silver in red, the manganese catalyst in blue, and the solid blocks are carbon monoxide, the dashed blocks is hydrogen. So you can see that the Faradaic efficiencies are repeatedly better for our silver electrode, but because we've got a higher current density, our partial current density for our manganese electrode is significantly better. So we're pretty pleased with this. This has gone into a wider pattern some years ago now, and the paper's sort of been bouncing around for a little bit now, and hopefully you'll see that soon. And it compares pretty well to what's out there in the literature. There's one other manganese catalyst on a gas diffusion electrode from Carlo Nervi's group where they do far more elegant chemistry. Like they actually understand how to do chemistry, so they covalently attach this to the surface, whereas we've literally deposited ours down in the polymer mix. So what happens now at lower pH? Well, we can change the electrolyte out. We can put in a pH 3 buffer, and we actually get improved CO Faradaic efficiency, so that's really good. We thought we might. There's a huge caveat with that this is only lightly buffered. We know the local pH is much, much higher. We can run the experiment for a very short time before we're having to adjust the pH. So it's interesting, and it gives us a clue it might work. Downsides, the manganese catalyst degrades over time. So after 5 hours, it seems to catastrophically fail. We switch it off and it comes back. And we think that we understand that now. We think it might actually be the local pH changes and we're going too high. So that's an interesting point. The silver you can see is much more stable. So it's an interesting species, but it's not perfect. But let's see what happens now if we put it in an acid CO2 electrolyzer. How am I doing for time, by the way? What time do we start? Okay, fantastic. So we thought about a number of ways of doing this. We could just take a standard PEM electrolyzer structure like you'd use for hydrogen evolution and swap out the cathode and put in our CO2 reduction electrode. But we've started getting interested in what's known as a bipolar membrane electrolyzer, and these have got advantages and disadvantages. First of all, what are they? Well, for those that aren't familiar, a bipolar membrane is made up of an anion exchange layer sandwiched to a cation exchange layer. The advantage of this is that you can have different pHs at each electrode. The way they operate is that we're going to use it under reverse bias operation. So at the anion exchange, cation exchange interface, we're going to get water dissociation, and we're going to take protons across to our cation exchange layer, and current's going to be carried by hydroxide at our anion exchange layer. So if we now contact our cathode directly onto the cation exchange layer, so we're going to use what we call a zero gap operation structure, which is beneficial and can potentially give quite high current densities. We're going to have a very low local pH for our cathodes. It's going to be nice and acidic, which is what we want. And the good news is we can then have an anode which is operating at high pH, and we know that for water oxidation, of course, we've got a limited selection, really a selection of one. I would argue for water oxidation catalysts at low pH, which would be iridium oxide. Here we've got the world to choose from. Lots of different things. We could put just a nickel mesh in if we wanted it to work particularly well. Everything comes at, and the other big benefit, of course, is that we will potentially still get a bit of carbonate formation. It is possible local pHs could rise high enough at high current densities, but we won't get much crossover. So carbonate will not transfer efficiently through the cation exchange layer. So there's a lot of benefits. The downside, it incurs a large voltage cost. Certainly if you use a commercial bipolar membrane, as we are here, the overpotentials you induce can be quite large for the water dissociation, and there's also quite a large resistance loss in the commercial membranes. But there's some beautiful work in the literature from sort of Tom Maluk and Shannon Bosch's group who are bringing these right down, these potential losses, and it's very promising. So they're getting a lot of interest for particularly photoelectrochemical systems. Of course, you can see the benefit of having the photoanode, photocathode at different pHs, and also for electrolyzer systems. When they've been used in this reverse bias mode for CO2 reduction, they've generally given just very, very low Faraday efficiencies for CO2, under sort of 10%. The sort of standout examples come from Tom Maluk's group a year or two ago now. But here what they did was change the pH and brought the pH back up of the cation exchange layer. So they made it into a weaker acid surface at the top by modifying the polymer structure and building up in a layer by layer way, which means you get the selectivity, but of course you're still going to have the carbonate problems. They brought it back up to pH 7, 8. So what happens if we put the manganese in that? It's a bit of a disaster. Bit of a bombshell, that. Fortunately, this isn't quite the end of the talk. So we get very, very low Faraday efficiencies, actually lower than we get with silver. And I'm going to be honest here, this is a pure water feed. This is quite a cool cell. So we're literally just feeding water and humidified CO2, no other salts. The reason we feed water to the anode and use a ruthenium oxide catalyst rather than deliberately going to very high pH at the anode is just that in a bipolar membrane you can get something, you can get small amounts of Cowan transports if you put in other salts, and we want to minimize that to really see the intrinsic behavior. So we've worked with pure water. So we get lots of hydrogen, not much CO. So we're not clear why that's happening, but the good news was we had another project running in parallel. Otherwise, I wouldn't be talking about it. And again, this dates back to Gaia, who, as a PhD student, spotted something in a catalyst that we'd developed for sticking onto photoelectrodes originally. And her project was taking nickel cyclams, a known CO2 reduction catalyst, and modifying them so they adhered to photoelectrodes. And her catalyst we've used with POW to make some photocatalysts, which was very nice work. And the Reisner group as well, we've used these a couple of times with as well, and they're very nice CO2 reduction catalysts. This carboxy one doesn't really adhere too well in water, but what's interesting is it doesn't have this planar structure, of course. It's got a structure which we believe enables this carboxylate group to interact with the active site, either of its own one or of a neighbouring one. And when you protonate this carboxylate group at very low pH, we see a large acceleration in CO2 reduction kinetics, and that was a very nice observation. We could get very good selectivities. Sorry. Okay, I thought you were saying 5 minutes, so that's fine. We can get very good selectivities for CO2 reduction. We get about 9:1 CO to hydrogen at pH 2. That's on a mercury pool electrode, which is rather fantastic. So we were delighted with this when we developed it, and I remember now the battles we had with reviewers, them saying, well, it works in acid, why do I care? You need to care. And they were going, no one's ever going to do CO2 reduction in an acid. It's very satisfying now to see the literature. That's my smug moment. So it's a really interesting catalyst. It seems to work at low pH. Actually, the parent cyclam, we didn't big this part up, obviously, because everyone's trying to get their paper published, actually works at pH 2 as well. It's not as selective. It's just under 1:1. And you can see it's I haven't actually shown it here. Here's the observed rate on a rotating disk electrode experiment for our modified cyclam. You can see it's got quite high turnover frequencies. It doesn't show this large acceleration that the normal cyclam does. Sorry, the modified cyclam does. But it's still in itself a very good CO2 reduction catalyst, and it's incredibly easy to make as well. You can buy cyclam, you can buy nickel salt, you put it together. It's quantitative, it's a macrocycle, it just sucks the metal up. So now let's put this in our bipolar membrane electrolyzer. So same device as before, nothing too complicated. Down the bottom you can see I've done some XPS just to show it is the nickel cyclam on the surface. Not going to go into that in detail. Not sure how well people can see this. There is nickel present. We deposit at 1 milligram per square centimetre for the nickel, and we've actually compared that to a silver electrode at 4 milligrams per square centimetre, because we found if we did the silver at any lower, we just got such terrible current density, so we made it harder for ourselves. The amount of nickel catalyst that's active is tiny compared to the amount we deposit. That's mainly because we deposit currently with someone with an airbrush spraying it, and half of it goes across the bench. It's also got a very low electroactive coating loading. We've tried to put carbon fillers in to improve it. It doesn't. I'll come to that in a second. So there's only about 10% of the catalyst actually active, but it's still enough. And what happens when we run this thing? So there's a lot of data on this slide. So black is the silver catalyst. So if you look at A, there's the Faraday efficiencies. Black's the silver catalyst. Hashed is hydrogen. Solid is CO. And you can see that silver starts at low current densities with no CO being produced. And as we expect from sort of Mark's work, as we increase the current density for the device, as CO Faraday efficiency starts to increase up to sort of 20, 30% at moderate current density. So we're at 100 milliamps per square centimetre now. The cyclam catalysts behave quite differently. So here we are at 12.5 milliamps per square centimetre, 25. We're getting in excess of 60% Faraday efficiencies for our cyclam catalysts. And actually, this is a time-dependent Faraday efficiency. If I look at very early times, it's up in the 80%. So our catalyst is working with really quite high selectivity. The Faraday efficiency starts to drop though as we increase the current density. And that makes sense for a number of reasons. Primarily, it's the fact that we've only got a low electroactive loading. When you work out the number of catalysts present, and you work out the max turnover frequency, we're maxing out the catalysts quite literally. We just need more operational catalysts on the surface. So partial current density stays the same, Faraday efficiency drops as the total current density of the cell increases. Cell potentials are pretty rubbish, but we're not going to worry about those. I'll come back to that. So we're pretty pleased, but there's problems. Nickel cyclams are curious little catalysts. So they're present in their nickel 2 state at open circuit. We reduce them. They form nickel 1 cyclams. That's the active CO2 reduction catalyst. They go through their catalytic cycle. They produce carbon monoxide. They then have a binding constant for carbon monoxide, which is 10 times that of carbon dioxide. That's a problem, so they self-poison. If you form the nickel 1 carbon monoxide, it knocks the catalyst out temporarily. You can then take it back by lowering, making the potential more positive again. The CO will be released, you're happy. If you go further negative, you can reduce the nickel 1 carbon monoxide and irreversibly destroy the catalyst. So at high current densities, this device fails much above 100 milliamps per square centimetre, pushing it too hard. Under normal operating conditions, we can see this self-poisoning, this irreversible self-poisoning, and we can lower it by increasing the flow rate of the CO2, so we dilute the CO, so that's pretty nice evidence. We can also turn the system off for a few minutes, and we see the CO recover. And now we're actually finding we can pulse the electrode, which is quite cool. And so we can actually operate this and keep the Faraday efficiency pretty high for prolonged periods. So they're not ideal catalysts, but you can see we can maintain Faraday efficiencies well above 50% for CO production, and this is in a strong acid environment. And that is pretty unique. So if you want to read this paper, because it's out as a preprint, we're remarkably, should first be at round 4 of review. So read the preprint, because it might be a little while. So it's an interesting catalyst. It's not the perfect one. It's more about proving the point that the molecular catalysts might offer the sites, and we can use these then as models to try and identify other ones. So we know, for example, we can make analogues of the nickel cyclam based off single nickels into carbon nitrogen materials. They're well-known catalysts. You can have a look at the work of people like Peter Strasser who make these, and they're wonderful. So, last few minutes, can we overcome the deficiencies of this catalyst? Well, can we increase the electrochemical area, active area? We tried to do something pretty simple. Synthetically, it's not so simple. You put a pyrene group on the catalyst. You kill some of the catalytic activity, though. So here's the parent catalyst at the bottom. Really big current enhancement under CO2. You put the pyrene on, the current enhancement decreases. Note the scale. It's about 10 times lower. And we know that that happens. That's pretty normal when you modify a cyclam. You muck up its structural flexibility, and you also take away one of the key amine groups which are involved in the catalytic cycle. But we do get very high surface coverages for this catalyst, and we can put that in a gas diffusion electrolyzer. This is actually just a near neutral one, and it works okay-ish. The big problem is that as you operate this thing, you have to push it to much more negative potentials to get a decent turnover rate, turnover frequency, and the pyrene actually desorbs. It doesn't help that much because we think you're just reductively desorbing the pyrene. So yes, we can increase the electroactive content. I think we can do it in much smarter ways than this, though, with these systems. If I've got 2 or 3 minutes left, can I finish up on? Yeah, super fast. So just drawing in some work from SEAFUEL. So obviously, we're working towards trying to make these things work better, but we shouldn't just think about the cathode, we should think about the anode. At the moment, I'm just using a ruthenium oxide anode. Can we actually now try and improve the device further? So we do a little bit of work on oxygen evolution catalysts. This is actually done a lot with Maulik Patel at the University of Liverpool and his colleague Suraj Gupta, and also the team at University of Mumbai. And we're interested in boride catalysts. So you take a boride catalyst. Here we've got a cobalt iron oxyboride. You put it into your electrolyte, and this would be a high pH electrolyte, and it forms a nice oxyhydroxide shell. You get a nice conductive core. And you can see that you can change the metal content. We can get particularly high activities now for OER at high pH, and we can compare our behavior here to a standard non-boride catalyst of just the oxide, and it's much improved. And I think I'm being told to finish up, so I'm just going to skip the last part, apart from to say these are also really interesting. And this all fits into the bipolar membrane electrode story because that's chloride tolerant. And that's why we studied them as part of the SEAFUEL project. So we can run these in the presence of sodium chloride and still get very good Faradaic efficiencies for oxygen evolution. So in principle now, we could have a device, I'm not sure why you'd want to make it, where you put seawater in it to the anode and just humidified CO2 into the cathode. And they've got very low over potential. So that's kind of fun. We'll skip that last slide. I just want to draw some conclusions. So CO2 reduction, I think we do need to start thinking more about the carbonate problem. We might be able to work at high pH, but we've got to change the device structure and modify it slightly if we're going to do that to overcome these losses. An alternative is to work at low pH, so let's try it. There's lots of smart things we can do with the existing catalysts, but why don't we have a look towards the molecular electrocatalysts and see if these can do something? And I think we're showing that these can be very effective. Obviously, we have issues. They're not perfect. These are not devices that you're going to go out and deploy anytime soon, but we're learning a lot about how to make this work. With that, I just want to finish up and thank everyone. So this work's been funded a lot by the UKRI Circular, it's a horrible name, Interdisciplinary Centre for the Circular Chemical Economy. A lot of the work was started by Gaia as a PhD, then as a postdoc, and then we've had Mark and Pavan who have done a huge amount as well, and more recently Kathy. And we're grateful really to our collaborators at a number of different universities. So thank you, and look forward to, I don't know if we're doing questions now or at the end. Thank you.
Hello. So I was just curious about this final part of the presentation regarding these borates, which look quite interesting. Have you maybe tried something with in acidic pH with these catalysts for oxygen evolution reaction?
So, yeah, these borides are really interesting because you make the transition metal boride and then you put it into your electrolyte, and they'll basically form a sort of a porous oxide type structure on the surface. So at low pH, these will just dissolve away. So they don't work at low pH. We can take them down to sort of pH with the cobalt-based ones, so a cobalt oxide, you can go down to pH 5, 6, I think, before it starts to decay too much. But then it becomes a self-healing catalyst as such. So we try and keep these at the high pH. If the low pH, there's people far more qualified to talk about this. There really is a dearth of catalysts available. We have iridium oxide, and even that is not fully stable. There's not much else that's stable and active, unfortunately. It's a very tough problem.
Thanks. Very nice presentation, Alex. I was, I guess, related to I was wondering if there is any like nickel iron oxy boron.
Yep.
I don't know. And also, a second question is, which is the active layer that you mentioned they form?
Yeah.
They form oxyhydroxide.
Yeah.
Who is the catalytic?
It takes a second to catch up. The first point, yeah, I believe the nickel iron analogues have been studied. We've worked solely on the cobalt ones with Suraj, but yeah, the nickel iron ones are known. I wouldn't like to comment which is better. The OER literature is littered with problems in the, I think this, sorry, I'm going to jump around slides a bit to catch up. What you can't see because of the resolution is that this is a plot down the bottom here of catalyst loading versus overpotential. You can see that, just look at the number of different catalyst loadings out there in the literature. So benchmarking catalyst 1 versus catalyst 2 is something that as a community we just need to get much better at doing and standardizing. So I wouldn't like to say what is better and what isn't. Apart from clearly we've fixed the criteria, so ours is the best, as everyone does. Back to what the active site is. So we can see a clear correlation between the onset potential and the sort of minimizing the over potentials for sort of the 10 milliamps per square centimeter for the formation of the sort of cobalt 2, you know, that cobalt 2, cobalt 3 oxidation pre-peak. So clearly it appears to be that cobalt site, exactly the same as you see in a cobalt oxide catalyst. And what we're seeing here is actually the beneficial behavior of the core. I think we're just seeing a very thin shell of active catalyst and then the core supporting the device. So I think it's like having a very thin cobalt oxide catalyst over a conductive core. I don't think that there are interesting catalysts. I don't think we've fundamentally changed the chemistry of the surface, despite some papers saying otherwise. Okay, thank you. No, perfect, thank you.